invitations from Chen. So my name is Brian. So we're part of the Human-Computer Interaction Lab. So officially it's called the In the Wild Lab. So it's actually called by one of my colleagues, Matthew Pike here, also the assistant professors from the School of Computer Science. And we also have Huang Liang is from the Department of the Electronics and Electrical Engineering. So both of them are part of this project, which is the smart sensing in firefighting, so which involve both the hardware and also the software developments. That's why we have kind of collaborations from two different schools of the department. Okay, so just to begin, so we started these projects I think 1 or 2 years ago. So the whole background about the study is we talk to the firefighters and then to understand what is the current situations of the firefighting conditions. So as you can see from the statistic point of view, a lot of the sacrifice from the firefighters, especially around the big fires in the forest. Like a few years ago, the forest fire in the Sichuan that caused a lot of the firefighters' casualty. And so based on the policy support from the government, the Chinese government itself, so they are encouraged how we can integrate these smart types of the sensing into the firefighters to increase the safety of the firefighters. So comes to our study. And we also look into the economics of the market size of these firefighting equipment in the global markets worldwide. So I think the most more advanced of the equipment has been utilized quite a lot mostly in the USA, less in the Europe, and also less in the China. Part of it is that all these equipments are very expensive, so it's introduced very high cost for the developments, high cost for the research, high cost for the investment. So even nowadays, a lot of the equipments that are used by China firefighting or China firefighters department are still all the equipments are buy or bought from the USA. So there's quite less of the currents of the equipment that actually develops in China itself. So all those suits or everything are actually from the USA. Okay, so just evolutions of what is the current equipment they have been using now in the firefighters. Until now, most of the things they are using now is called the PSSS, the Personal Alert Safety System. So in this system, basically it's very hardware type or hardware oriented. You have a lot of the goggles, straps, the belts, the wristband, the fires resistant suits or everything. So as you can see, a lot of this is not very smart. It's all based on the materials, based on the very simple way of alerting the firefighters about when there are problems. So at the current point, the parts they are using now is a very small equipment they put on the shoulder here. So inside this equipment, they only have one very simple motion sensor. So what that means is that if you fall down, if you are not moved for 30 seconds, then it will sound the alarm. So it's very simple equipment. It doesn't really shows you any informative information. So one of it is that when we talk to the firefighters, they have the issues of locating the firefighters that trapped into the fire scenes. So they have no ideas where are the firefighters, and also there are problems if they are in the buildings or in the facility with a very heavy smoke. So what they want is that how we can able to identify the locations of the firefighters in a quick way, and also how we able to communicate with the firefighters in the indoor environment. So this is some of the things that are very concerned they want to solve their immediate problem. So the three major immediate problems they are looking into is what happened inside. So where are they and how we can communicate with them. So this is the main things they want to resolve. So this is where we come in and see what we can do to help them to solve the problem. So the first thing that we come into is, of course, related to the problems. One is, how do we know what is happening inside? So what is happening to the firefighter inside? What are they doing inside? And what is their current positions, or what is their current motions or current activity they are performing inside? So from the wider point of view, this is related to human activity recognition, which is called the HAR. And the common technique that we have now, of course, is the computer vision, which is a very popular approach. And we also have the sensor types, and also we have the variable types. So we try to test. Well, vision type is definitely not meaningful, because if you are in the heavy smoke, basically it can't detect anything. So we have to switch to the sensor base. And from the sensor base, HAR itself, a lot of study has been conducted. So you can see there are different ways of putting, or different positions they can put the sensors on the body. Some of these popular ones, for example, they put it on the head, in the chest part, upper arms, the waist, the legs, and the body. So these are some of the ways of they put the sensors to detect the human activity. Okay, so the first thing that we come into is the first version that we actually tested out 2 years ago. So we actually implement a very simple one, just to put the sensors on the existing of the what they call as the PPE, personal protection equipment, which are on these suits. So the main idea is we don't really focus on the hardware design, but focusing on activities they want. So the first activity they are very concerning is about, how do we know actually when the firefighter is fall down? So they want to know how they fall down, or like types of the way they're falling down. So we tested a lot of different ways of how they're falling down. So the way they fall down is to the front, to the back. They fall down on the left, on the right. And at the meantime, we also found that there's quite a lot of the activities that looks like fall downs, but it doesn't actually fall. So we include like these 3 types of the fall-alike type activity, just to remove these kinds of the false alarm. So eventually, this is something that will come out called the VRRN algorithms, to actually detect the firefighters whether they are falling down. So at the same time, we also went through the numbers of the motion sensors that put on the bodies, on the different parts, like which of the combinations of the individuals that actually produce the higher correct accuracy detections of the falling. So as you can see, so the C, everything I think believed to, sorry, which one? The chest, the elbows, the wrist, the thigh, and also part of it's on the other ankle part. Okay, so there are like 5 of the positioning. So as you can see, although we have if you use all the sensor data from all these motion sensors, you can see the accuracy can be very high. But then we also look into what happens if you just able to use the limited or the less number of the motion sensors. And we found out that actually, if you put a sensor on the chest part, it can actually produce a very high accuracy already, compared to if you use the all combination. But this also only limited to detecting the falling. If you try to detect different types of activities, then we need to different positionings of the variable sensing. And then we also come up with a very simple positionings of to show, like a very brief, to show to the commanders outside, like what happened, or like the current positionings or the simultaneous motions of the firefighters inside. But this is very brief, and eventually they think that this is not quite useful to them. So I mean, based on their stakeholder point of view, so they don't really need to know everything about the actual motion. They only care about whether they are facing dangers within the fire scenes. And then we took the further step, focusing more on the hardware design. And then they requested, like, in the ways that, what happens if you want to wash the personal equipment? So is there any ways that we can, remove the sensors, and then we can wash the shirts, and then we can put in the sensors again? So this is the one we came out with the knuckle type. So you can put in the sensors and remove the sensors. But eventually they also think that this is a bit troublesome. Okay, and after discussion with them, they think that eventually, why don't we just implement something easy, some things with the variable sensings that can just wear anytime. It's easy for them to remove, easy for them to wear. So they're actually not preferring this type of the design, but they're just preferring just using the variable sensing. So from after several types of the testing. So so this is some of the things that we tested in the laboratory, and then we move on to further redesign, refine the sensing. So we come up with our own design now, including the IMU is the motion sensor, EMG is the sensing for measuring your muscle strength, and HR is your heart rate. So we integrate three types of these sensing modules within one single component, and then we bring it to test to the firefighting training scenario. So they use this when they do the training scenario, which we are able to detect around 8 different of the activities. So this is the positions of the doing the testing or the training actually. So including all these different 8 types of the training. We are so eager that we want them to bring into the actual fire scenes, but this is not allowed. It's again the policy. So they are not able just to use the sensors that we developed and then bring into the fire scene. So the only experiment that we can do now is during their training. So this is and then from these models, modelings, or the computer science part, so we take some of the what we call a hybrid machine learning network. So we implement some of this network to detect some of these sub-activity. So the sub-activity here, you can see that the activities of all this movement, then we further divided into the upper body and also the lower body. So because we have the sensings on the upper body part and the sensings on the lower body part. So we do some experiment and do some testing, whether we can further separate them into the upper body and also the lower body. So from here, you can see that all this activity, they are actually combinations of difference of the upper bodies and also the lower body action. So for example, if you look at the A1, it's actually the sub-activities for number 1, and also the A5 also exactly similar, which is the upper body action number 1. But then the lower body for the A1 is number 3, A5 is also number 3 here. So this caused a bit of problems that you can see they are actually quite the same. Okay, so eventually we will have to do back a similar way of using combinations of the different sensors to see what actually constitute the difference of how we can differentiate them. So eventually we also found that the highest of the accuracy, of course, is to take all the sensing data into consideration. During the experiment or during the testing, we found that the muscle strength is actually useless, actually pointless for them, because all of them doing the training or the strength training every day. So basically, the measuring the muscle strength doesn't able to detect the action they are doing, because their muscle strength is much more higher than the normal person or the normal user. So this doesn't really, demonstrate the way that how their strength can produce much more meaningful on activity recognition. The other one that we also tested on the, as you can see just now, our sensing also including the heart rate. But now when we come to the analysis, we don't include the heart rate, because we also tested that based on the commanders or based on the firefighting scenario, eventually we thought that if they want to complete the training, they have to do it fast. They have to run, they have to do it in the high intensive mode. But we are actually the opposite way, is that when they do the training or when they do the firefighting rescue, they are not encouraged to do running. So part of the reason is they want to save how to optimize the energy tank, how to optimize the energy consumptions they have. So they want to maximize the time for them to consume the energy, consume the oxygen. That's why they are not going to run, they are not going to do very activities that increase the heart rate. Okay, so eventually, so this is something that will come out, and we are able to produce the higher performance for the activities compared to the existing state-of-the-art methods. And then we take a bit further, and then we look into the individual's performance. Then we found that some of the firefighters actually produce the lower accuracy or the lowest performance compared to others firefighters. So one of the reasons when we look back into the videos, then we found that for example, the firefighters number 12, actually you can see that it's actually performed the wrong action when they do the training. So this is the correct way that you're supposed to drag the rescue person, you're supposed to drag by pulling them, and you have to walk backward. But this firefighter, as you can see, is doing in the wrong way, that it actually pull the person rather than pull the person and you walk forward rather than he walk backward. And similar also on pulling up the hose from the higher levels of the building. So the correct one is you should only stand and then you pull. But these firefighters, just to save the energy, he just pull the wires and move back at the same time. So this is wrong. So in that case, that's why it produces lower levels of the activity recognitions. So we take that further, and then we can think of how we can use this information so that these information can be used for assessing the training performance of the firefighters in the future. So some of the papers that we submitted, or some of the high qualities of the journals that we submitted, so they are sharing some of the concern is that there are not many papers or not many studies in the worldwide regarding to the firefighters. Is actually you get the data from the real fires or from the real fire scenes. So we actually talked to them. He said, can we actually burn something? Can we actually create a much more realistic fire environments? So this is what they told us, is that every time they need to burn something, it costs a lot. Okay, so if they want to burn the buildings, because they install all the equipment on the buildings, including the cameras, everything, if they burned it, everything cannot be used, and it costs at least 300,000 for one time of the experiment. And for this one time of the experiment, I think most of the case we only can take like 3 or 4 of the firefighters' data. So if you want to take like 100 of the firefighter data, you can imagine how much money we need to burn. Okay, so in general, well, they said this is not practical to them, so we are actually now also not able to take the real data in the real fire scenes. And then for our next research, we are focusing more on the indoor localizations and the mapping. I'm not sure whether you are familiar with the indoor positioning system, but so one of the things about the firefighter is that they want to know what is the motions or where is the locations of the firefighters. If we look into the existing of the IPS that we have now, the most popular one is of course using the wireless sensor network, where you place the sensors on the building, within the buildings on the ceiling, for example. And the other one, you can use some of the sensing method. So this is the visual base, where you can scan while you're walking. So, but these two are very intensive. First one, when you need to do this kind of the deployment, you first need to deploy all the sensors in the building. So which is impractical for the firefighters because you don't have time to deploy. And the second one is based on the vision base. And again, the problems with the vision base is there's a heavy smoke inside, so it's not practical. And then we move into the what we call as the dead reckoning method. So this is based on the motions, the speed of your walking, and also your angular rate, the change of your angles when you walk. So it's depending on the speed and also the orientations of your walking, which is the DR. So we look into some of the existing scientific problems for the DR. So one is potentially some of the sensors that we're using, most of the case of the sensors that we're using, they have this cumulative positioning error. So what this means is that at initial point, if there is an errors that cause when you're moving, and the errors will keep increasing. So this is the problems that we're trying to solve. Of course, if you are using a very good sensors, some of these problems may not exist. So the good sensors that we look into, one of the motion sensor that can produce less of this error, it costs around 3,000 RMB for one motion sensor. So what we're trying to tackle or to solve the challenge is how we can use a very cheap sensors like 50 Kwai, and then solve these cumulative errors. So again, so this is just for the background. So this is the some of the top study about the DR methods over the past few years. So this is the red one is our study, so which is what we have starting and what we are doing now. So basically, the ideas of using the dead reckoning is based on your to indicate your leg movement. So your leg movement usually we consider into two. One is called a swing phase. So swing phase is basically your leg is swinging, and the other one is the stand phase, means your legs is standing on the ground. So as you can see, if you are in the swing phase, your left hand of your legs is not on the ground, and the stand phase is your leg is on the ground. So we use some algorithms of this to determine whether that your legs is on the swing phase or on the stand phase. So this is all the algorithms that we have, and then including this GRRT and also the average filters to filter the noise from the sensor. And eventually we come up with a threshold to determine whether you are in the swing or in the stand phase. And then this is the experiment that we've done. As you can see, this is the closed loop, which is the popular of the evaluation methods for doing the testing. So the main point of this is that, as I mentioned just now, because when you walk, the sensors will produce the error. That means if you walk in the closed loop, originally you won't able to get a very nice closed loop because the errors is increasing. So one of the data I can show you, not this one. Oops, I didn't put in the data. Sorry, I didn't put in the video. I think you can look it here much more. Sorry, it's a bit not clear. But oh, sorry, as you can see here is that you start from here, but then you're walking because of the errors is increasing. You are not able to close the loops. So the algorithms that we introduce is eventually we are trying to close the loops so that it reduces the cumulative error. And then this part is with the introductions of the ultrasound sensor. which allow us to do the very simple mapping about the structures of the building. So not much of the things that about the ultrasound sensor. So as you can see, as you walk in, it kind of generates some of the boundary of the building, so we know about what is happening in the building. And yeah, so that's basically this part. And then the next part that we are working now is that, now imagine this is only for one person, for one firefighter. So next we want to look into, imagine that there are 3 different firefighters entering the building from 3 different positions or 3 different entrances. So how we can actually put them together under one single map. So to do that, first thing we need to look into is this magnetic fingerprint. So I believe that everyone, all the humans, everyone have the unique fingerprint. So this magnetic fingerprint is also unique for difference of the devices in the building. So for example, if you are walking to that elevator, or if you have the devices like computer, you have the devices in different buildings, each of these devices actually produce a very unique magnetic fingerprint. So we use this magnetic fingerprint to indicate where are you in the current building. So to use this magnetic fingerprint, we are able to fuse different maps from different firefighters into one single unified maps. So this is the overall process, starting from the identify the magnetic fingerprints data, and then we find the region of interest. So this is basically to see which part of the devices or which part of the building that actually generate the magnetic fingerprints that is useful for us to extract. Okay, and so we tested on 2 different of the scenario. One is we tested on individuals scenario, which means, as you can see, so this is the original data that we collected without applying the algorithms on the filtering, and this is the one that we corrected the position after applying the filters. So you can see that we are able to close the loops. So this is the problem that I mentioned just now. So this is the first round they're walking, and then this is the second round they're walking. So as you can see, although you are walking in the same building, in the same positions, in the same trajectory, but the output, as you can see, are different because there is a cumulative error here. So this is what we're trying to do, is to solve the problems of having when you walk 2 rounds, it's able to put you back in the same position. And then we do another one for 2 different persons. So the first person, you can see the red one is the first person, and the blue one is the second person. They actually started from 2 different positions. And then eventually you can see there are two difference of the errors, or two of the bias between the first person and the second person. So what we're trying to do is, are we able to put these 2 together based on the magnetic fingerprint, so that we know that they are actually in the same building, they are actually in the same positions, they walk through the same ways. Okay. So this is all we come up with. Basically focusing more on this particle filter optimization. So how do we do the correction? Okay, and so this is just adding into the ultrasound. You can see to identify the boundaries of the way that we're walking. Okay, so that's basically the whole thing, and then we now have experiments on doing the multi-person. So different person, A and F. So what we're trying to do here is we have 2 different persons walking on the same positions on 2 different days. So we want to identify whether this magnetic fingerprint works on 2 different days. Okay, so it works well. Our errors that we propose here is the lowest compared to the state-of-the-art study. Okay, so that's basically for the indoor localizations and mapping in the non-vision base. So one of the problems with this, although in the top journal as well, is that lots of the journals, they are not able to install the cameras around the large spaces to get the ground truth. So for example, imagine like for this small room, if you need to install very high quality of the cameras on this room to get the ground truth data, presumably you will need like 9 cameras in this room. It will cost you around 500,000 Chinese yuan to just install this to capture your ground truth data. So this is something also we're trying to solve in the futures. Third one, focusing more on the internet part, solving the communications between the indoors and the outdoor environment. So this is something that we come up with in what we call the Internet of Firefighting. So I understand that you are not from the networking area, so I'm not going to dig into deep about this. But this is some prototypes that we are building, able to switch between the 4Gs, 5Gs, and also the Wi-Fi and the Bluetooth, so it can transfer the data from the inside to the outside of the building. Okay, so for future works, so taking of what we have now, we talked to the firefighters, and the firefighters are very interesting. Are we able to come up with the training assessment framework or the training assessment platform? So from what we understand now in China, whenever they do the firefighting training, everything is based on observation. So there is no systematic way for us to evaluate how good when the firefighters is doing, or how good is the performance of the firefighters training. So this is the next step that we're going to look into, of course from different areas, from their stress analysis, from their mental workload, and also from their attention awareness. Okay, so I guess that's all for me today about the smart sensing in the firefighting. Anyone have any questions? No?